Today we are going to discuss how can we use machine learning to predict organic reactions. And I'm going to specify what do I mean by prediction of organic reactions. Later, we also will discuss several case studies that I find exemplary in such a way that they illustrate common tasks for machine learning in organic chemistry. So before we begin, I should show you this slide because as a rationale for using machine learning in organic chemistry, and the reason why should we aim to predict organic reactions is the overwhelming diversity of organic compounds and organic reactions. And the reason for this is the so-called combinatorial explosion. Like if we have one reaction, then we may variate, we may change it a little bit and conduct it under different conditions. And if we plan some organic synthesis, then the number of possible synthesis grows exponentially. Like if we have choice only of two variants, we already are going to have a great number of potential variants after several steps. So the same goes with organic compounds, as I will later show you. So let's discuss organic reactions in general and specify and define several important terms that we will see are indeed really important in the field of applied machine learning in organic chemistry. If we taking an organic reaction, we have reactants by the left hand and products by the right. And we always should distinguish reagents and reactants. And this distinction is very important, as I will show later. And if I confused reagents and reactants, as I can, and many Russian-speaking people can as well. So you can always correct me, and so good of you if you will find any confusions by my side. So reactants are consumed during a reaction, while reagents participate in the reaction and include catalysts, inhibitors, or promoters, solvents, some additives, etc. And this distinction is very important. So here, for example, it's quite we have only one reactant, However, water here, the definition for the water molecule is blurry. So is it reagent or reactant? And speaking of objectives for machine learning in organic chemistry, I will name several. First one is to predict products from reactants. This is a common task, and it's a textbook task for organic chemistry students. So here we aim to get an artificial intelligence that solves a simple task. Yeah, I think so. Such a definition. Speaking of machine learning models as artificial intelligence in this context may be indeed relevant. So first, we may aim to predict products from reactants. Next, we may aim to predict reaction conditions. And this is in fact very important, as I will show you later. So also, we can select a more complex task to predict reaction products from reagents and not from reactants. Not from reactants only. So we include catalysts, solvents, etc. And this is in fact a more complex task, as was shown in several papers I will mention later. And also there is another task that is much more complex that we are going to discuss in the next lesson, and that is to predict organic synthesis or retrosynthetic pathways for a given target molecule. So this task is discussing this task will be a pinnacle of our course. So today we are going to discuss the first three tasks for machine learning in organic chemistry. There are several reasons for the observed great diversity of organic compounds and organic reactions. And as well, since these reasons are highly related to the complexity of machine learning tasks in organic chemistry, let's discuss them before discussing ML applications. So first, organic carbon in organic compounds forms very strong carbon-carbon and carbon heteroatom bonds, and it allows this element to be a framework to form frameworks of a great number, infinitely great number of organic compounds. And also, as you know for sure, there is the phenomenon of isomerism. So isomerism leads to complexity of many tasks due to so because of the isomerism, we need to deal with structural formulae, and this leads to complexity of many tasks. So there are many types of isomerism, and there is the first type is the isomerism of functional groups. So we may have molecules with the same molecular formulae. However, their reactivity differs qualitatively, and as for example, can be observed for organic peroxides or the case of alcohols and ethers. And there is, of course, the isomerism of the carbon framework, and we can have isomers with different arrangements of double and triple bonds, as well as we can have different isomers of different cyclic isomers, for example, etc. And also we should mention spatial isomerism, and there are, of course, enantiomers, which are mirror images of each other. So you cannot, these two molecules are basically different, so we cannot transform one into another without breaking carbon-carbon bonds or carbon heteroatom bonds, or maybe distorting the molecule very substantially. There are also diastereomers, so these are spatial isomers which are non-enantiomers, like E and Z enantiomers, or we can have more unusual cases, cases with diastereomers that more unusual cases of diastereomerism that are caused by the presence of small cycle in the molecule. So we can even speak of conformational isomerism, and in this case we need to specify temperature at which we observe a given molecule. So if we consider, for example, this 1,2-diodoethane molecule, this rotation around the carbon-carbon bond will be very rapid at ambient conditions. However, if we cool down our system to really low temperatures, maybe even below the boiling point of liquid of nitrogen, then we can observe individual rotamers like here, here, and the rotation around this bond that proceeds very rapidly at ambient temperatures will be really, really slow. And there is a great diversity of various organic reactions that is related to the diversity of organic compounds. So to name, there are many classifications of organic reactions that try to capture this diversity, and you can follow this link. So there is fairly there is an adequate article on the Wikipedia. So if you feel yourself as beginners in organic chemistry, you can try this one. And there are several classes of organic reactions, like addition reactions, eliminations. So when a molecule or a species or a reactive species is eliminated, substitutions, reductions and oxidations, and even so we can speak also for rearrangements, etc. So there are many variations to every single class listed here. And what we really need to mention is reaction efficiency metrics. So given the complexity of organic molecules, there is we cannot specify one perfect metric for every organic reaction, and selecting only reaction yield is not enough for sure. So we can speak of chemoselectivity when during the reaction only a specific functional group reacts. We can speak of regioselectivity when a specific type of bonds, arrangement of bonds is formed. And we can speak of diastereoselectivity if we get only one diastereomer during a reaction, or we can at least get one of diastereomers in excess. And we can also speak of enantioselectivity. So we get either this or that enantiomer in excess. So in addition to reaction yield, we should always consider reaction selectivity as in the vast majority of organic reactions, we should consider reaction selectivity in addition to reaction yield. So after having discussed all this, let's discuss some notable case studies in the specified field. So the first study is on using machine learning to predict suitable reaction conditions. And this task is, in fact, of paramount importance, because even small changes in reaction conditions can make a reaction unsuccessful, in the sense that we can get zero or a really low yield, or we can get non-stereo-specific reaction. And also, if we consider machine learning tasks, specifying incorrect reaction conditions can lead to wrong reactivity predictions. So predicting correct reaction conditions is, in fact, a very complex task, as I will show you, as I will demonstrate you later based on this example. And let's consider such a table. So as we here, as we see, we have a catalytic reaction of catalytic functionalization. So we introduce a functional group with a catalytic system that includes a transition metal catalyst, a base additive, and also here reaction temperature is also important. So varying these conditions affects reaction yield to a significant extent. Okay, if we see, so we see that prediction of reaction conditions prediction is an important task. However, it's a challenging task as well. And there are several challenges related to reaction conditions prediction. The first one is that basically it's very hard to predict all reaction conditions. And mostly we are interested in all reaction conditions because of the second challenge, which is that reagents, reactants, and solvents are interdependent. So if we specify only a subset of reaction conditions, then we may have a great number of potential conditions of other potential reaction conditions, like if we specify a catalyst for reactants, then selecting a solvent or proper additives, promoters, can be a really hard task. And next, there are problems related to data. To solve a machine learning task, a supervised machine learning task, we need to have data with catalysts, solvents, and reagents assigned as such. And such a data set is very challenging to construct for a number of reasons. So you can refer to the original article for discussion. And it's also difficult to quantitatively assess the level of correctness of conditions. And there are problems related to representation of the chemical context. And so last but not least is the problem of the inherent bias in the chemical literature, in the chemical scholarly literature, because chemists usually expect some types of reactants and reagents speaking more generally, to be reactive in particular context at particular temperatures and pressures. So usually experimental works map only limited subspaces of the chemical space, and taking only experimental data from articles may lead to unbalanced data sets. So in the work using machine learning to predict suitable conditions for organic reactions, a team of researchers proposed a machine learning model based on an artificial neural network, and this model allowed them to predict reaction conditions that included a catalyst, up to 2 solvents, and up to 2 reagents, as well as it allowed them to predict reaction temperature with some accuracy. So they consider only single product and single step reactions, and this was done to make the problem tractable. I have also, so I suggest you to read this article, and you may find it in, so it's open access, and you may find it in the suggested reading material for this lecture. So they trained the artificial neural network on about 10 million examples from the Reaxys database, and they obtained an impressive accuracy for such a general task. So the model made a number of suggestions on catalyst, solvent, and reagent choice, and among top 10 suggestions, there were correct predictions. So I need to there were correct predictions nearly 70% of the cases. So here I need to specify what do I mean by correct? These are conditions that were selected in the data set they constructed. And their model also allowed them to predict temperature. So they constructed the data set in the following way. They preselected temperature in some adequate interval. So many reactions were basically multi-step, so they sorted them out, as well as they sorted out multi-product reactions. And they used smiles to encode reactants and reagents. So data points are entries that missed smiles strings were discarded as well. And so they used RDKit to work to construct molecular representations, of which I will tell you later. And they also sorted reactions that were out of the specified types by the number of solvents, reagents, etc. So in such a way, they obtained the data set. And they used smiles to represent initial molecular structure, and reagents and reactants were assigned, were explicitly assigned. So they used RDKit to construct Morgan fingerprints, and they calculated reaction fingerprints as the difference between product and reactant fingerprints. So catalysts, solvents, and reagents were treated as one-hot vectors. They also added the null class to account for absence of reagents or catalysts, etc. And they split the dataset in this way, in this proportion. So a little recap. I've told you about molecular fingerprints before in the lecture on molecular descriptors. So to represent molecules and specifically to represent particular types of atoms and functional groups in molecules, we can use molecular fingerprints like this. You can follow the link for the more detailed description in the RDKit manual. And basically, by selecting an iteration, we include more and more information on atoms in molecules and their surroundings. So if on the 0th iteration, we include only information on atoms, then by iterating further and further, we include information on atomic environments in such a way that each sequence of numbers encodes particular type of atom, its bonding, and its molecular, its intramolecular environment. So by constructing these by constructing these fingerprints, we get vectors that encode molecular structure. So the authors of this article used trained an artificial neural network of which schematic structure can be represented as here. So it's feed-forward network that in which layer with fully connected layers and several types of activation functions. So they used Gregorial cross entropy for data represented by classes like catalysts, solvents, and reagents, and also they used mean squared error as the loss function for temperature. And here they used a scaling factor to join these two. So you can follow this link to read the article on categorical cross entropy, as long as we don't use ANNs in our in the practical part of our course. I leave it to suggested reading. And what's important here is that the task of catalyst, solvent, and reagent selection is done sequentially. So after several layers, the catalyst is selected. And after selecting the catalyst, the model selects or proposes candidates for solvents and reagents. This is done exactly because reagents are interconnected. So for some catalysts, only for some catalysts, some solvents are efficient and allow to obtain a working catalytic system, while for other catalysts, other solvents are necessary. So they obtained they trained a model that allowed them to predict catalysts, solvents, and reagents with an impressive accuracy. And what should be mentioned here is that correct prediction of optimal conditions, a simultaneous prediction of optimal reaction conditions, is a much more complex task that than is to predict only one or maybe two reaction conditions. So basically, we need to inaccuracy rapidly degrades because of the multiplication of errors or probabilities. So their model allowed them to make impressive predictions of reaction conditions in the cases of rather complex and currently popular organic reactions, like, for example, selective reductions, selective hydrogenations, or amination reactions with a palladium catalyst, and cross couplings, metathesis reactions, etc. So all these reactions employ really complex catalysts and precise set of reaction conditions, including additives and solvents, as well as the temperature may be quite far from ambient. So what's important here also is that the authors provided an online tool that allows anyone to predict reaction conditions given reactants and products. So let's consider an example. Like, for example, this one. So we input two small strings, including the smallest representation of an acetic acid molecule and that of isoamyl alcohol. So this product has a specific order of pairs and some organic chemistry practical courses include the synthesis of this as one of the tasks. And let's hit submit. What do we see here? So basically, this model suggests us to perform this reaction without a catalyst and solvent, and use sulfuric acid as well as to perform the reaction under slightly elevated temperature. And there are some weird suggestions like performing this reaction neat, okay, without any solvent and catalyst. We can also use hydrochloric acid, and we can use dehydrating agents. So for a simple reaction, we have a number of obvious and useful suggestions. You may tinker at home further. So let's discuss the second task related to reaction regioselectivity prediction. And I need to say several introductory words related to this particular task. So there are two approaches to reaction prediction, and the classic one is the so-called template-based reaction prediction. So these methods identify reaction centers and propose possible transformations based on predefined rules, emulating a human expert. This is a classic approach, and sometimes it works very efficiently, especially given a very diverse set of predefined rules. And in the recent years, there are some models employing the second approach were proposed. And so the second approach is the so-called template-free reaction prediction. And in this approach, molecular structure is treated as a graph or sequence of tokens. And I will tell you what do I mean by the sequence of tokens a little bit later. So given this task of electrophilic aromatic substitution of the regioselectivity prediction in the case of EAS reactions, we all of us remember that these reactions are quite simple and widely used. They occur where they proceed according to simple mechanism that gets a little bit more complex in the case of a substituted molecule. So if we consider ortho, meta, and para sites, which site will be the most reactive given a particular functional group, given a particular R And the task in this work, for which I provide a link, and I strongly suggest you to read it because I included it into suggested reading material. So in this task from the Drug Discovery Journal, the authors predicted a bromination site in organic molecules from inorganic molecules, and this data was extracted from the Reaxys database, as I will mention later in more detail. So before considering this task, we need to discuss the problem of classification with unbalanced classes. Why should we do that? So in many organic molecules from their data set, the situation, the molecular structure was so that unreactive sites are much more common than those that are reactive. So basically, we can have only one site that is reactive in a given molecule. And this gives us a classification task with unbalanced classes. So the null model under which considers all sites as unreactive or non-reactive had a very decent accuracy of 76%. That's why the authors used Matthew's correlation coefficient as the metric of accuracy. And the formulae, it has quite complex formulae that includes the well-known metrics as precision and recall, and it combines them in this way. While null model has accuracy of 76% MCC, taken as a metric of accuracy, MCC provides a correct estimation of 0% for the null model. They used an original molecular descriptor that a link to which you can find in the presentation I've sent you, and they provide code to compute these descriptors that employs the quantum chemical method GFN1XTB. And as you may remember, we used the second generation of this semi-empirical method before GFN2XTB. So this semi-empirical quantum chemical method is used to compute atomic charges in a molecule, and taking these atomic charges in the following fashion: atomic environment is encoded. So we select the query atom for which we want to predict the probability of organic electrophilic aromatic substitution. And we encode molecular environments by using the Can-Ingle-Perlock rule. So we select atoms by increasing molecular weights. First, we select the nearest neighbors in a topological fashion. So we go from one molecular graph node to the neighbors, to its neighbors. And we select hydrogen, next this carbon and sulfur. So the obtained vector includes atomic charges, and in such a way we get a vector descriptor that encodes its environment. So the authors used the PyCorel library that allowed them to compare several machine learning algorithms, and they for the final model they selected LightGBM. The authors presented the learning curve, and for those of you who are interested in the details of model training, I suggest you to read supporting information for this article, just as the article which is open access. The authors compared the accuracy of their new model, which they called regioML, with several limit boundary cases. So basically a null model is unpredictive, and they also trained a totally overfitted model that basically remembers all data from the training data set. So one nearest neighbor, and expectedly its performance is rather low upon generalization. And also they compared their previous results with so they compared their previous model with the new one, and you may read about this Regio SQM20 model that employs more intensive quantum chemical modeling. So they their model basically gave output in a form of probability of electrophilic aromatic substitution in particular sites. And if the probability was higher than 50%, then this site was considered as reactive. You can get the code on the GitHub, and also there are there are links on the dataset, and on the details of model training, I especially suggest you to download and tinker with the dataset. Another case we should discuss today is the prediction of outcomes of complex organic reactions. And there are two articles related to this task, from which the first one is in the first one, the prediction is treated as a translation problem. So if we consider smiles if we select smiles as representations of molecular structure, we can treat them as texts. And in such a way, the prediction is translation from texts representing reactants to a text representing products. For this natural language for such a task, there are natural language processing algorithms, and basically authors adapted NLP techniques to the context of organic chemistry. So they took the data from the USP2 dataset, and data there encodes. So this dataset includes information on reactants and reagents and products in a mapped way. So they transformed this data in several steps, and the key step here is the so-called tokenization. So after specification of reactants and reagents, sequences describing chemical reactions were tokenized to be processed by a neural network that was trained. So tokenization is a very general approach used in natural language processing, and we can speak of various types of tokenization. You can follow the link I've provided here that describes various types of tokenization. And in our context, the authors tokenized molecular smiles representations into parts describing atoms and bonding. So they trained a complex deep neural network with which you can get familiar by following the links I've provided before and here. And basically, the deep neural network utilized the so-called attention mechanism that allowed them to highlight reactivity sites in tokenized sequence, in tokenized forms, tokenized representations of reactants and products. They used data from US patients. So we should mention several limitations related to this model. And the first one is that generated strings may in fact not be valid smiles. I have never found such a situation. However, by using the online platform which uses this model, we need to mention that the second limitation is that multiple product reactions couldn't be treated. The authors developed this approach later. However, their model later and took a little bit took a different approach. So you can refer to this article and see what improvements were offered by the authors. And now let's see how the online platform can be used to predict outcomes, products of organic reactions. So let's select some reactant and let it be something that we have discussed previously. So let's predict the outcomes of an aromatic electrophilic substitution. And here we go. So we get structural formulae and smallest representations. So you can try it later. Here so now we have discussed the cases I wanted to highlight, and in the end, I would like to mention that there are several data sets of organic reactions that you can download and use in your research. So these data are freely available. If you want to tinker, go ahead. I thank you for being here today.